Some time ago, I think before I got involved with this, the folks at DWave set their sights on building a quantum computer based on quantum annealing of a programmable transverse field Ising spin system implemented in superconducting flux qubits for largely two reasons. The first is that appears to lend itself to attacking a wide variety of problems across a lot of disciplines, a lot of problems that people care about. And secondly, that system to all of us seemed at the time, and still subsequently, that with then available technology, that it would be possible to implement it and start attacking these problems with real systems. Both of those suppositions have largely proven out for us. So since that time, DWave's focus has been on developing quantum computers to provide value to customers, to solving people's problems. So my first assignment when I got to DWave in 2005 was to design a superconducting integrated superconducting integrated circuit that had two qubits on it coupled together, and then to work with my colleagues then to test it and understand how start to learn about how quantum annealing would work. By the time we've gotten to the 2,000 qubit processor, the DWave 2000NQ a few years ago, beginning of 2017, I'm not designing any chips anymore. We have smarter and better people to do that. I'm not testing them anymore either. We've got more and better experimentalists to do that. But those folks still let me hang out with them, and I'm still work with that team. And now I'm involved with the team, leading the team to develop the next generation product, the Advantage, which I'm going to tell you about in a couple minutes. But I wanted to go back and show you over time. I have a plot here, semi-log plot. On the vertical axis, I'm showing qubits plus couplers for demonstrated quantum annealing systems. And then the x-axis is time. The choice of the y-axis is this is a slightly better representation of the complexity of development and also of something about the effectiveness of it. It's not the best metric, but it's a better metric than just showing qubits. Since the first commercially available and delivered quantum computing system, the DWave 1, back in 2011, and indeed from a couple of years before that time, we've been able to get this technology out to third parties, to folks who are not physicists, who are not experts in quantum computing, who are not at DWave, who are interested not in how quantum annealing works, although some of them, but also they have their own problems that they want to solve and are interested in looking at new technologies to solve them. And as we progress through from the DWave 1, the DWave 2, 2X, 2000Q, we've progressively been getting feedback from folks that are using the system. And we've found that this has been extremely helpful and valuable towards getting perspective on, well, what's easy, what's hard about programming this system, what works well, what doesn't work well. And as we've gone, sort of reflected on all of this, and basically the point of the next generation system is to incorporate as much of this as we can into this product. So the DWave Advantage is built with this customer feedback in mind. Again, with the main focus, the sole purpose of that is to provide value to folks that are using it. We've learned a number of other things along the way. I think we all believe, and I think actually many, at least some of you do also, I think I've heard, that the first quantum application that provides value, the first quantum applications that provide values to folks will be hybrid in their use of quantum mechanical and classical computational resources. And I think we've learned that it is going to be developed, or these are going to be developed by folks who are not physicists, most likely, who are not involved in building the quantum computer, or even at a company that's building quantum computers. Everything that I'm going to talk to you about our approach and our strategy, are based on those premises and those learnings. So the next generation product, the DWave Advantage, again, is built on top of, at the core, a new quantum processing unit, a QPU, that's got more better connected, quieter qubits. So this will have more than 5,000 qubits. It'll have 40,000 couplers. Each qubit will be connected. I have programmable connections to 15 other qubits, up from a degree 6 connectivity. That was the basis of our previous 4 generations of technology. And this is really about making it easier for folks to be able to map their problems onto the fabric of this processor, about making those mappings more efficient, which in turn results in better performance. And of course, being able to attack larger problems that are more likely to be at the scale of commercial relevance. Yeah, so an example with the new processor for the 8x8x8 cubic lattice that was featured in Richard Harris's 2018 science paper on doped spin glasses that I'm going to touch on in a few minutes. We would be able to embed a 15x15x12 lattice with the new technology. Now, as much as I'm going to be talking to you about our go-to-market strategy and our approach as the business, I'm going to have a hard time hiding from you that I'm a technologist at heart, and I really have to comment that this QPU that we've developed has more than 1 million Josephson junctions on it. And for those of you that are maybe familiar with your Apple 5 chip that has, in your iPhone that's got 1 billion transistors in it, then maybe that doesn't seem so impressive. But if you're familiar at all with this more esoteric technology, superconducting integrated circuit, that's actually mind-blowing. 1 million Josephson junctions in a commercial product. It's got 110 meters of wiring, of superconducting wiring, that's about 1/4 of a micron in diameter, about 1/200th the diameter of a human hair. Maybe not that important details, but to me that sort of makes my hair stand on end. The process, QPU, is built on a lower noise technology, and that's about, so you can think about that as longer coherence times. We think about that a little bit differently. But that turns in, for a number of reasons, that turns into better quantum annealing performance, in a sense more multi-qubit tunneling, but also it allows for better problem specification, precision and problem specification, and ends up speeding up calibration. This is an important part of the technology. But getting back to the point I was making on the last chart about the importance of enabling development of hybrid applications by folks who may not be familiar with the technology, who may not be familiar with a superconducting flux qubit, we're developing this whole system with the idea of performing well with hybrid algorithms, hybrid applications. And so to that, we also are reworking the operating software to support that, including lower latency within the system, including other scheduling options. And also, more importantly, well, not more importantly, but additionally, I can't overstate the importance of this, more software and tools for the developer on the front end, so open source tools, and we'll talk about that in a second, to basically enable folks to make it easier for developers to understand and how to develop on the technology. So how do we make this system available to people? It's been a little bit over a year since we launched Leap, our cloud service, through which you can access our technology. This is, to our knowledge, the only real-time cloud access, quantum cloud access. So you can self-sign up, you can get a free trial, and you could submit problems and get them back in seconds, in real time, without any person intervening. At the front end, on your laptop, you can download the Ocean tools. I guess I'll touch a little bit that on the next chart. But also in this cloud platform is a place where we basically are making available tools to visualize what's happening, a lot of documentation, a lot of examples. There's community support. There are places where you can post questions. Sometimes somebody from DWave will pipe in and answer. Sometimes somebody from the community will. And this is really all about delivering the technology and making it accessible to folks who may be developing hybrid applications. Any one of you can go and download our Ocean software development kit. It's open source. It's available DWave's GitHub repository. And we see this is basically an important platform to build on top of the basic API. And again, depending on it supports, the idea would be that if you were a developer and you would be working in one or other on an application, whether it was optimization or constraint satisfaction or a sampling-based application, you would then build that up on top of Ocean software. Actually, of course, you could work on the native API, but the advantage of working with Ocean is that it's got a more uniform sampling API. You can have as the back end the quantum processor, or you can use your CPU, or you can use GPU resources. And this is constantly being updated. It has in it descriptions and embedding tools that will help you. You could grab it now and you could see how your application maps into the next generation processor as well as the current one, if you're familiar with those, and get a heads up on how the technology is going to improve. I was going to give you a couple of examples of folks that have been developing applications and interested in engaging with the technology. Just a month or so ago, at a web summit in Lisbon, Volkswagen had developed a hybrid application, which basically involved a global bus routing optimization for a series of buses that were running at this conference back and forth around town and to and from the conference facility. Each of these buses had a bus driver, had an iPad, and it had GPS on it, and it had a map. And as they drove around, they were given alternate routes, options, and suggested directions to go. They, going into a little bit more detail, the head of our marketing department excoriated me for including this bright yellow chart in my presentation. It's not on brand, is what she said, but I'm including it. I insisted on including it anyway, with great gratitude towards Volkswagen and Shir Yarkoni at Volkswagen for sharing it with me and letting me show it to you, just to dig a little bit deeper into what does this example look like. So there was a application server that interfaced with the folks in the buses and their iPads with the navigation program. Those bus drivers are shown up at the top there. Goes into a hybrid algorithm, which would then take that and combine it with other external sources on the web, including, when are ferries arriving that are going to dump a bunch of cars onto the roads and increase traffic in certain areas? Where are the other buses? Where is traffic going quickly? Where is it not going quickly? And then doing a global optimization, so as opposed to where Google will route us all into the same road because the traffic is light there and we'll all show up there and make it crowded. This was done in a more collective and global sense. And then that problem, that binary quadratic problem, was then decomposed, and depending if it was simple enough that it really wasn't worth shipping back to Burnaby, it would just go to a classical optimizer, but if it was of a complex enough scale, then it would go to the QPU in Burnaby, and we were getting these in real time over the course of the demonstration, and so of course the system had to be up and running the whole time, our network connection had to be up and running the whole time. It went through our Leap system and into a system that was running in Burnaby on our cloud. Anyway, I think that the folks at Volkswagen will come out with a much more detailed description of this in the future, but this was a great example. It was quite recent. I think this is, to my knowledge, this is the only real-time quantum mechanical hybrid application that's been done. I might be wrong there, but that's the only one that I know about. There's another example. General Electric Research is looking at, so GE is a big company. They have lots of really interesting and big problems. They develop lots of large, heavy equipment, lots of engines, machinery. They also maintain and work on those. They repair them. And the challenge of dealing with that through, you have a heterogeneous set of vehicles that are coming in some asynchronous way to be repaired. They're in various states. There are various facilities that are required to repair them. Some equipment needs to be sent to several different facilities in sequence. You have certain trained operators that are able to work on different pieces of equipment. You have a supply chain of spare parts that are necessary. This is a very large job shop scheduling problem. The full-scale problem that GE faces is well beyond the scale of the technology that's available for it, certainly beyond the scale of our QPU. And yet they boiled it down just to look for proof of concept. Can we pose this problem with this technology? What does that look like? Is that awkward? Is it infeasible? And then what they're also looking at now is that, okay, but now can we use a hybrid approach in conjunction with quantum technology to attack this problem, and what does that look like? I'm going to talk about a very different type of application, and this is one. I saw there was a picture of Richard Feynman on the banner for this I saw this out there for the conference. This application is really much more along the lines of Richard Feynman's original articulation of the benefits of quantum computing, that if you could have a quantum system that was programmable, that you could get control of, that you could introspect, and that you could then, through physical metaphor, use this to evaluate or predict what another physical system that you were interested in was doing. Could you do quantum simulation with a quantum system? And the last summer, there were a couple of important papers came out. The aforementioned paper with my colleague Richard Harris, looking at doped spin glasses and cubic lattice. And then the one I'm showing here with Andrew King and some of my other colleagues, reproducing and doing a quantum simulation of Kosterlitz-Sallis physics on a two-dimensional system. So the significance of the two papers, the two works that we talked about in 2018, was really around accurate quantum simulation of two and three-dimensional quantum magnets, spin systems, and some fairly interesting and exotic physics. But in the intervening year, Andrew turned back to this work and said, well, okay, let me ask a question. If I was going to try and replicate this simulation using classical hardware, and I would need to use some kind of quantum Monte Carlo approach, and in fact he had to do quite a bit of that for the original work, how long does it take to do that? How much computational work is required to do that? And he already had an idea because he had to do this a lot when he was running the original simulations. And what he found was, and in here, this is discussed in this preprint that I'm showing here, so please go and look at that for sort of more coherent and cogent details about the work. But he basically teamed up with some of our friends at Google to really take a careful look at this question and make sure that we were doing the best thing, the most reasonable and clever way of doing the quantum simulation using the classical hardware. And he found that for large regions, or for certain regimes of this simulation, that the quantum simulation was millions of times faster than what could be attained with classical computing. So that's significant. Now, this is a very different type of applications than the one I was showing you previously. This is not an optimization problem. This is quantum simulation. But it's one where there's a very clear and compelling case of improved performance using quantum technology. I'm just going to touch on a couple of other ones. Menton AI is a startup company that's using the technology to do drug discovery, actually protein design, and find that using even our 2000Q processor, they're finding some improvement or benefits in some cases over the existing tool that they're using. Cogniframe is another startup that's looking at this technology for asset liability management. It's a very different type of application, but it again, and starts off as an integer programming problem, but it actually seems to map itself well into quadratic unconstrained binary optimization. OTI is really heavy into doing computational quantum chemistry to design their optical LED or component parts of their optical LED development. And they've been involved heavily in using not only DWave's technology, but I think a few other quantum technologies as well. Airbus, I think, was interested in fault tree diagnosis. Rather than dwell too much on these, maybe I'll refer you to every couple times a year, we have a user group meeting, Qubits user group meeting, where we get a number of folks to come together who are trying out the technology, who are interested, who want to understand how it will work in their enterprise, and they'll come to this conference, and we'll all talk about what they're trying to do, and we'll talk about where we think we're taking the technology, and we'll listen very carefully to what they're telling us. I really enjoy going to those because I always learn a great deal. A lot of those presentations are made public afterwards, and so if you go to, I think the website is qubits.com, and you can get access to presentations by, I think, a number of these folks going back to a number of the user group meetings. So obviously that takes time. You'd have to be curious and interested about that. But if you are, that's an avenue to go into more detail. There are many of these applications. I just want to touch on one observation for, okay, how do we think about where this technology may be providing value? And this is getting back into the context of sampling and optimization-related problems. And it's a question about the difference between getting a good solution and getting the very best solution. And this is a chart that my friend and colleague Kathy McGew provided for me. And I'm very grateful for that and for the work that went into this. So this is just looking at a particular class of problems, AC3 problems if you're interested. This is a native problem. And comparing how quickly, if I'm going to start sampling, I'm just going to program the problem onto the processor and then start taking samples. And then I'm just going to ask myself at each moment, what's the best answer that I've gotten to date? What's the lowest energy answer that I've gotten so far? And I'm plotting that on the left. And in the red plot, the red curve is that for, I think, our 2000Q processor. And in the blue curve is that for a best-in-class classical algorithm that was being used. And the striking feature, but one that apparently repeats and recurs in different forms, but in essentially the same message, is that initially the quantum technology will get a very good solution relatively quickly. And then eventually the classical technology will overcome it eventually. We'll eventually find a better answer. This is very often the case. It's not 100% always the time, but this is a recurring pattern that we've noticed. And so that if on the right, what we're plotting here is, say, what is the expectation, a mean number of samples that's required for me to get, well, the best solution, I would see for the quantum, here the color scheme has changed, and I apologize for that. Color scheme is different. They're both for quantum annealing. And the red is asking what's required to get the very best answer, or a lowest energy answer. And that as a function of the input size. And the input size scale is not number of bits. I apologize for that. It's a bit of an awkward axis. It's actually showing number of qubits, square root of number of qubits divided by 8, or some such thing like that. And so you could think about it as the lateral dimension of an array. As the scale of the problem gets large, the number of samples that are required to get the very best answer grows very rapidly. But if you're looking for in this case, number of samples required to get to within epsilon, where epsilon is 0.05% of the best answer, that stays a little bit more better behaved. Now that's a native problem. So all variables represent by individual physical qubits. A real application, there's usually a penalty associated with embedding. And so you may have a string or a cluster of physical qubits representing the variable, and there's a performance penalty for that. But even in that case, apparently that there's usually within, I think across all classes of problems, we end up, for real applications, tending to see something like within 90% of optimal in this way. So very quickly get to a very good answer, and then it depends on, so that's sort of talking to a regime in which there's some applications where, yeah, but that's not what I want the very best answer. So that's different. So this is if you need a very good answer quickly. Now let me shift gears a little bit and just talk a bit about getting back to the beginning, if we're not developing the application at DWave, who is? It's going to be somebody at a company who cares about the technology, who's interested in it. How do we get this out to that developer? How do we get this technology out? And it's a multi-tiered approach. First of all, through Leap, self-sign-up, free trial, lots of information available for enterprising developers. We're putting a lot of effort into resellers. We just yesterday had an announcement about an agreement with NEC, which included, among other things, that they would be a reseller for the DWave cloud technology. We've also recently announced an agreement, or QC Ware announced an agreement where DWave would be included in their Forge cloud service. And we had recently an announcement with Amazon that our technology will be available in Amazon Bracket. So these are just examples of basically working with resellers to get the technology available to more people through more channels. So bigger than just DWave, for sure. And then, of course, we have a sales team which focuses on cloud agreements at various scales. And also, we still sell physical systems. And have recently announced, actually, a sale agreement with Los Alamos National Lab to install our next generation Advantage system there, and as well as actually at Jülich, the national lab in Germany. We will be installing a system there afterwards. So maybe I'll just leave you with this, is just to encourage you to, this is a logo from our Leap service, our Leap cloud service, to try it out, to go sign up. You all get a free minute of time on an actual quantum computer. And a minute actually goes a long way. That doesn't mean that you have to start your stopwatch as soon as you log in. That means that's in terms of the total integrated number of problems that you can run. And you can still sign up, and even after you've run through your minute, you can get more for free, a minute every month, if you link your GitHub account at which you're developing excellent code that use the technology and link it to the